Good afternoon. So thank you, Alexei, for the introduction. Can you all hear me, or is it okay? Good. So yeah, a couple of words about. I started with an engineering background. I graduated here in Paris from Telecoms Paris Tech, and then did a PhD in what was not called artificial intelligence, but in digital image processing and pattern recognition. And then I did some work on the R&D side, both in academia and also at IBM. I moved to Switzerland to teach as assistant professor at EPFL in Lausanne. And then I went to the business world, joined HP. I actually spent 7 years in sales, where I first had sales rep, and then I was sales manager. Then I spent a few years in merger and acquisitions, and then moved into university relations. During 7 years, I actually managed a large team doing university relations worldwide for HP. In 2011, I joined Google to take care of university relations in Europe, and I did this job 6.5 years. And last November, I actually left, decided to do something else, and since then I've been consultant with a couple of customers in Switzerland and also in France, and also teaching a little bit. Okay, good. So that's for the background. The objective of the session is, and that's my goal. I hope this will be achieved and you will enjoy this. The idea is to understand how machine learning and AI work first. What are the basic principles under which this works, and their current applications and also limitations. Really would like you to walk away with the idea about what works, what is about to work, and what is, out of reach or even science fiction. And that's important for business environment. So there are two parts corresponding to the two sub-sessions. In each part, actually, I'm going to have a little bit of close to math presentation to show you how it works, and we are going to have also a business side to explain the applications and so on. In the first part, after some quick intro, we are going to do a very simple, perhaps the simplest examples you can have in machine learning, and we are going to see a system working to actually do automatic mortgage decisions. We are going to imagine that we are in the retail bank and we have to take these decisions automatically, and how this is going to work. Then we'll go back, step back a little bit, and talk about AI, the history, the hopes, hypes, some first major business successes which happened during the past few years, and also the current limits and also pitfalls. Then in the second part, we'll talk a little bit more about machine learning and do some examples. I will show you a playground on which you can actually dive a bit more and run some machine learning cases. And we are going to, however, to concentrate on the main developments in AI in the industry today, and what are some of the differentiation factors between the companies and their approach to AI. Okay? So if you have any question, just don't hesitate. I would like this to be interactive. I'm going also to ask you questions so that it becomes lively. Don't hesitate. Really, I'm here for you. Okay, so a machine learning system would actually take some data that you have, learn out of it, and then use this learning to do predictions based on new data which would come. Here is an example. You want to build a filter in your email to detect spam. So for each email, you would like automatically the system to tell you whether it's spam or not spam. So most of the systems in machine learning are going to work using two phases. The training phase, in which you give to the systems, you are going to give a set of emails which are already classified as spam or not spam. And you're giving this to the system in order for the system to learn. And the system will look at these emails, will look at who sent this email, what is the content of the email, are there attachments on which you click and then you get a huge virus, blah, blah, blah. And make some knowledge out of it. And then in a second phase, once the learning is done, the system will be used to do predictions. New emails are coming. You don't know whether they're spam or not spam, but the system will tell you this is spam, this is not spam. So 2 phases. The first one is learning and the second is prediction. How do we make learning and prediction for a given email? We do this by using what we call features. Each email will have features, and features can be some words in the email. It can be the address of the sender, the date at which the email was sent, the origin, the location from which the email was sent, the IP address, whatever. These are the features, and these features are used for the training in the first phase, and later also for the prediction. Okay, so these are a few words to introduce the machine learning. So now let's go immediately to the most simplest method you can think about, and which is actually used by many businesses in machine learning. It's called the KNearest Neighbors. For this, we are going to take another example. Let us assume we are sitting in a retail bank agency. And in this agency, actually, customers are coming and they are asking for a mortgage because they would like to buy a house or an apartment or garage or any piece of real estate. So we are going to make decision based on a few features. So what can be the features of a customer? Well, for example, the price of the house, the income, the yearly income of the person. What else could be used to make a decision about giving a mortgage? What could be other criteria?
Guarantor.
Sorry?
Guarantor.
Yes?
Any collateral they already have.
All right, yes.
Age.
The age, yes.
Credit history.
Yes. Okay, so you have many features. You can have also the number of rooms of the house, maybe the location where the house is. What else? How many features do you believe they could be like this?
Who already has a mortgage? Also, possibly.
All right, so how many features do you...
You don't have a mortgage?
Yeah. So how many features do you see to make a decision about giving a mortgage to somebody? Hundreds? Okay. Well, we're talking about tens. In systems, 20, sometimes 30. So hundreds is a bit on the upper side. Maybe there are some places where they... Anyway, in our example, we are going to, in order to be simple and to see really how machine learning works for this method, we are going to concentrate on 2 features. The first one is the purchase price, which means, how much is the house or the apartment. And the second is the yearly income of the person. And for the first phase, the training phase, we have a set of data which is coming from some colleagues or from some past history of the retail agency. And for this particular data points, we have, for example, for one customer, a given price of the house, a given income, and we know that for this customer the answer was yes. So we put here a green cross, okay? For this second customer here, this is the purchase price, this is the income, it was also yes. For this particular customer, the purchase price was here, the income was there, but it was a no. Okay, and this is our training set. This is what we are going to use, how we are going to use the system to be trained with using this. Now, let's go to the next phase. So plotting these different points is the training part. We have trained our system, and now the system can make the decisions. So we take a new customer showing up, and we want to make a decision out of our training set using for this customer. So this is the black cross here. And for this particular customer, we have a given purchase price and a given income. And this is the black cross, which is here. And the KNN method is very simple. It's about looking at the nearest neighbors and making the decision depending on whether we said yes or no for the nearest neighbors. So if we look at k equal 1, only one nearest neighbor, it's here. We see that the nearest neighbor is a green cross, so it's going to be a yes. Okay? If we look at k equals 3, so we look at the 3 nearest neighbors, and you see here we have 2 green crosses and 1 red cross. We're inside the circle. So it's still going to be yes. And for obvious reason, we want to take odd numbers, because if you take an even number and there is a yes and a no, you have a hard time making a decision with this method. Okay, so you can see that we can make decisions out of this very simply. It's very simple to implement, and we can go for there. Okay, so that's the k-nearest neighbor method. Now, what we're going to do is to apply it to a data set, which we are going to create using some bank data. Okay, so we are going to use what is called the UBS Mortgage Calculator, which is here. Okay, so UBS is one of the largest banks in Switzerland, and it's a bank, a retail bank, which is also giving mortgage to its customers. And they have online, and you can go to this. There is the link in the slides. Online, you can actually do a mortgage calculation, which means here you put the purchase price of the house, so it's in Swiss francs because it's in Switzerland, so you put here a price. Here you put your yearly income, and then you put the down payment you want to do, and it would tell you whether you're going to get the mortgage. In this case, it's going to be no, whether it's affordable or not. Okay? So this is what we're going to use to generate the data. Because for this particular, we can put here price, we can put income, and we have the decision from the bank already here. So using this, we can generate some data. So what we are going to do is actually to build a data set using this UBS Mortgage Calculator and automate the decision process using the method I just showed you, the KNN method. And we are going to perform the decision based on 2 features, purchase price, income, and later we'll introduce down payment in the example. Just to tell you the strategy we are going to use, we'll start from the simplest possible. So you're going to see that some of the decisions are very basic. But in machine learning, it's very important to start simple and to introduce complexity stepwise. Because if you start with a complex model and it doesn't work, you have a very hard time finding what doesn't work. Whereas if you start simple, you understand how it works, and then when you get more complexity, if it doesn't work, you can tackle much easier what doesn't work. Okay, so we are going to create the data set. I'm going to visualize it to show it to you. Then we'll construct the training sets, the test set to actually get the results of our method. We implement the algorithms and see the performance. All right. So, created the data set using the mortgage calculator. And the decision that we'll try to find is based on the UBS rule in this calculator to actually decide whether somebody is getting the mortgage or not, which is that the monthly cost should not be more than 1/3 of the income. So that's the rule. If the monthly cost of your mortgage is more than 1/3 of your income, they say no. And what is the monthly cost? Without going into too many details, it's based on the interest of the loan, on the maintenance cost of the house, and some amortization cost. So not necessary to be too detailed here. And here is a visualization. So here I visualize 500 samples. The yes are the green dots, and the no are the red dots. And here I have visualized 100 samples. What I would like to show you here already is that if you have lots of samples, of course the boundary, which is in this case a line, which is a linear boundary, is relatively simple to visualize. It's intuitive. Whereas if you don't have many samples, well, it could be linear, but it's not that obvious. Okay? And this is going to play a role later. Good. So now, to construct the training and the test set, we need to do a couple of things. I'll talk about normalization after, but usually in the old way of machine learning, people in the 80s, 90s, and early 2000s, they would say, we take 70% of the data in the training set and 30% in the test set. Today, if you work at Amazon or Google or whatever, you have millions of samples, billions sometimes. So usually 98% of your sample is training and 2% is test. But here we don't have many samples, so we'll stick to the first thing. Then normalization is very important because we are going to convert our features into values between -0.5, +0.5 with zero mean value. Why? Because what we want to do in KNN, we want to see who is the nearest neighbor, which means that we have one point here, which has where there is a purchase price, and then there is the income, and here we have a second point where we have purchase price and also a second income. And we want to compute a sort of Euclidean distance between both. But you know, the purchase price could be in millions, where the income would be, you know, 10, 20, 50 times lower. So we need to normalize this so that we compare apples with apples. Otherwise, if we do, you know, purchase, if you look at Euclidean distance, it's going to be and we take the square root of this, that's a Euclidean distance between these 2 points. If this is in millions and this is in tens of thousands, this is going to be in millions, or even square, and this is going to be in tens of thousands. So this one has no chance to make any difference. So we need to normalize so that everybody is in the same ballpark between -0.5 and 1/2. And it's going to be even more important if you have quantities with different units. So for example, number of rooms. If you compare millions for the price and then 4 to 6 rooms, no chance that the second parameter would make any insight in front of the first one if you don't normalize everybody to the scale -0.5, +0.5. So it's very important to do this, and it's a necessary step. So let's go back to the implementation. I don't want you to read code here, but just that you know, in order to implement a method like this, it's 4 lines of code. So the part of implementing is very simple. You have in Python or in R or in other languages, you have routines which are available, open source, and that you can use, and in a few lines of code you can really run this. So it's not a big deal to program.
Who's got some coding experience? Just checking. All right. Just 3 folks.
Good. Now let's see the performance. So here we are running this on 500 samples, 400 in the training and 100 in the test. So the samples in the training set are the dots here. You have the red dots, which are where it was refused, and the green dots where the mortgage was accepted. And I put them a little bit in light so that it doesn't, paint the whole picture. Okay, and then in the test set, these are the triangles, and the decisions according to the KNN rules are either red or green, whether since k equal 1, we are looking only at one neighbor. So for example, for this point here, it's green because you have a green dot which is very close. You have a performance rate of 97%, which means that only 3% of the times we are wrong. And this 3% of the time, which is actually interesting, correspond to places where the density of the points is not good enough. For example, this one here, which should be green, actually is red because the greens are too remote and the red is too close. But if you do k equal 5, you are going to have a worse performance, 95% accuracy, with 5% of the times where it's wrong, because you're looking at 5 neighbors. So if you take here this point, for example, you see that if you look at the neighbors, most of them are red. There is still one neighbor which is green, but it's not enough to make the decision. So here around this boundary, which is the boundary that we should find, you are good most of the time, but sometimes you're wrong because there is not enough density of training points. So that's an important factor.
Yeah, I just want to make sure that everything is clear. So
Yes.
The training sets are the dots. That's all of the data that you've acquired. The tests are the triangles.
Yeah.
And K is the number of neighbors around the triangles that you're looking at to see whether the mortgage passes or not.
Right. Who has a question at this stage? Is it clear for everybody? Okay, good. So you see, it's a very simple system, very simple, very straightforward to implement, and which does the work, basically. Does the work. 95% of the cases are fine with this. Okay. If we have more samples, then suddenly the performance is way much better. Here I visualize only 1/10 of the samples, but to compute this performance, I have actually used 5,000 samples. And which means that then it's very dense and there are no more errors due to the lack of training points close to our decision point. All right. Now let's get a little bit more into the fuzziness and randomness of human decisions. We are going to say that the rule of 1/3, the monthly cost should not be more than 1/3 of the income, is sometimes not taken as strict by the retail agency people, and they allow sometimes themselves 10% discretionary, which means that if the monthly cost is 1/3 of the income plus 10%, they still could say yes or no. So if we introduce this randomness, because it depends on either criteria, such as are they long-time customers, or do they have a lot of savings, or stuff like this, then if we introduce this, we are going to have a different picture. So here I have plotted the 5,000 samples, and you see that here you have some zone where you have a mix of red and green dots. And when you actually perform key equal 5, the KNN, you get a performance which is worse than what you got when they were much when this discretionary rule was not introduced. And you can see here, for example, that this green dot is this red test point is misclassified, and so on. So randomness does not help the method. The method cannot guess randomness. The method can guess a linear, very strict boundary, or any deterministic boundary between the dots, but it cannot guess randomness. It cannot guess that maybe it's yes, maybe it's no. It depends on the person who actually took the decision. All right, and changing K doesn't change much the picture. Here I've plotted the performance versus the value of K. We see that it's decreasing a little bit, but it's not very significant because we are talking about not even 1% from K equal 1 to K equal 9. So it's not that relevant. And if you stretch this to, even K going to 20, 40, 100, then it's relatively stable at 94%. All right. If you stretch the discretionary variation even more with 20% discretionary variation, then you get a performance which is much worse, 90%. And that's becoming bad. But here you have 20% discretionary, which means that if the monthly cost was 1,000, well, it could be also 1,200. So you see that the method is very sensitive to things which maybe a bank manager would allow. So you see a little bit the limitation of the method to deal with uncertainty. All right. Now, do we have a lot of data? Do we really have a lot of data? Because here we saw that we were making the best decisions with lots of data, thousands, of points. Do we really have thousands of people which are applying for mortgage? Okay, so to do this, we can do a back-of-the-envelope calculation to look at this. So in Switzerland in 2014, you had 3.5 million households. About 37% of them had the ownership of house or apartment, with about 300,000 new owners in 15 years, which means that there were about 20,000 new mortgages per year. Now, if you take UBS and Credit Suisse, which own approximately a third of the market, it means that for UBS, there were about 3,500 new mortgages per year in Switzerland, which is not a lot. And if you have one agency, you could have as little as 200 samples for 1 year. Which means that depending on the business where you are, this is not big data at all. This is a small amount of data. So the methods still perform, but with some boundaries, of course, with some limitations. So, in the conclusion from this is that the method does the work in most cases, even for small data sets, which is the case here. The normalization, choice of distance are important steps. It can be used for many features or dimensions. You can have many more features if you want. The method is the same. And the results are stable when the training set is dense enough. The value of K is marginally relevant, and the method is comparable to human behavior. Why is it comparable to human behavior? Do you know? Somebody wants to? Why is the KNearest Neighbors comparable to what a human would do? What would a human do to actually attribute a mortgage? Yes?
I mean, if the human's going to do it, he's going to look at who's similar in a similar situation, and he'll say, okay, these guys got it. He's pretty comparable, so we'll say yes or no.
Yeah, exactly. That's exactly the point. That's exactly the point. The method looks at the nearest neighbors in terms of similarity, which a human would do. So, which means that in a business situation, if you're using this method, you have a very easy time to explain to a customer or to somebody the method and how it works, because it's similar to what most people would do, which is not the case for many machine learning methods. But for this one, it's the case. So it's relatively easy to grasp. Now, we are going to step back now that we have seen these examples, and I'm going to do a little bit of explanation about artificial intelligence, where it's coming from, what are the trends, and so on. Peter Norvig is a director at Google and a professor at Stanford of artificial intelligence. He wrote many books, and also he did a very famous YouTube video. One is called How Computers Learn. I've put the link here, and I encourage you to look at this video. He would categorize artificial intelligence in 4 categories. 2 out of 4 are implemented using computers, and 2 are not implemented using computers. Let me start with the ones which are not implemented using computers. One is about thinking humanly. So you want to reproduce the human way of thinking. So you're trying to find how the human mind works. So we are dealing with psychology, with testable theory of human mind. So far, this is a branch of humanities which has not done much computing. Thinking rationally. Here you're trying to think using rational rules. So this comes from Aristotle, and this is called logic, and works, but the problem is actually that you don't solve practical problems. You solve theoretical problems which are in the mind of the people, but real situations is not handled. So these are the 2 where computing has not been involved so far. And now there are 2 where computing has been involved. First one It's called acting humanly. So you would like the system, the computer, to act as a human. I mean to really reproduce human behaviors and human decisions. So we are talking about natural language processing. The computer should understand the human language, understand reasoning, machine learning, and the holy grail, if you want, of this is called the Turing test. How many of you know the Turing test? Okay. Who would like to explain what the Turing test is? Yes?
The Turing test is a test to determine whether or not a machine can fool humans into thinking it is itself human. So far, it hasn't been beaten yet.
Exactly. Okay? So this is the holy grail. It's a sort of heaven of artificial intelligence aficionados, if you want. It's really about, you know, becoming as human so that people can be fooled with the answers. It's usually also associated with high-level computer vision, high-level robotics, and in films like Ex Machina, or for people from my generation, 2001 Space Odyssey, you can see that some machines are becoming human, not only for the best, not always for the best, but at least they're trying. And, but this doesn't work today. Today we're not close to this, and we'll see why after. Yes?
According to you, like, can we see this in this century, or is it something that is like not this century?
We'll see this. In a couple of slides, we'll come to this. And so it's a great question.
Have you seen Ex Machina?
Ex Machina, have you seen it?
Yeah.
Good movie.
Okay. Yeah.
It's really about like
Yeah.
the Turing test.
Yeah. The main character Eva, this female robot, is becoming ambiguous in terms of, is it a human, is it a machine, and how do we deal with this person, and so on.
And one last anecdote, if you have a Google Home or Amazon Echo, you could actually try asking them whether they are human and see what the answer will be. This obviously has been pre-coded. For instance, Google Home will say, no, I'm not human, but I got a D+ on my Turing test. So, good.
So, then you have acting rationally. This is the business approach. It's an agent, rational agent approach, and here you have a business problem to solve. You have a recommendation system, or you want to translate, or you want to recognize speech for any business. And you want to have the best expected outcome. You don't care whether it's going to reproduce a human, whether it's going to be close to a human or not, you want to solve your business problem. This is the main approach today. This is what everybody is doing with a lot of success, and it's called good enough. It's called good enough because what you're trying to achieve is really to solve one problem. For example, you want to recommend books. You don't care whether the system has human feelings or whatever. It's, you know, tell me which book I should read if I buy this one. And that's what works today. In comparison, which is a bit more questionable at the first line, and the other things which are more in the humanities field. Okay? Now, hopes and hypes. I've taken two images on top from 1900, and these two images are about the world in year 2000, so it's already overdue. And what you see here is a teaching machine, which is interesting because you have the teacher putting books in this machine, and students have a headset and they're listening. We have achieved this to some extent. Okay? Here you have a hairdresser of year 2000, which is a robot. So how many of you would like to go to a robot hairdresser? How many of you believe that it's going to be feasible to have a robot hairdresser and you're going to be fine going there? Okay, good.
it's easier for me.
Good. Yeah, we both went to this type of hairdresser, and we can sort of testify that we are nowhere near a good
We
result.
are guinea pigs.
Yeah, we were tough guinea pigs. Okay. In the 70s, there were two hopes. The first one was in 2000 Space Odyssey to have a machine which would have human feelings, and that's really HAL 9000 talking to the main astronaut. And the second was expert systems. You know, an expert, the system which would be actually fed by an expert, which would tell the system, you know, if I see this situation, I decide this. If I see this type of images, there is oil in this field, and so on and so forth, and reproduce this for business. Of course, it didn't work, but at least there were some very significant tests and trials in this direction. And today, our hype is ABBA in Ex Machina or her brain, which is here. And these are two different stories. Here we're talking about, you know, human shape and appearance, and here we're talking about the ability to put so much memory and so much computing power in a small ball like this for a couple of watts, you know, that you display into it, which is a huge challenge. Okay, recent successes. I just said that in the 70s and 80s it didn't work. There were not many business successes, which led to a sort of winter of AI. But AI resurrected from this winter about 10 years ago. And there have been a few significant business success. The first one you're going to study with Alexi, I guess, the ads and user information for online advertising. And that's
only the folks in my marketing class.
Okay. But, you know, the online advertising works according to assumptions made on the users, which are triggered by machine learning systems. Recommendation systems, we spoke about them. So these are huge successes. Billions of dollars have been generated with these successes. So there is really tangible business behind. And the entire industries are disrupted by this. You know, the advertising industry, the retail industry, these are huge disruption, partly due to the availability of such system. Here I've put in smaller fonts, things which work but don't represent large businesses as we speak. They might become, but they are still sort of nice to have. Speech recognition, machine translation, handwriting and text recognition, image tagging, image search, smart reply. These are things you like to have in a smartphone. Now, would you pay a lot for this? Maybe, maybe not. Who would like to pay for such things? Which means that there is more than technology to this kind of business problem. It must address a pain point. There should be people ready to pay for it. If you don't have this type of setup, maybe it's just nice to have.
Right now it works for people who receive a lot of email,
right.
And the pain point of having to answer just yes, let me think about it, etc. You know, it takes like 30 seconds, and for these short answers, it's perfect, right? But if you want the more elaborate answers, it's not that good function.
So now I would like you to do a little exercise. Here is a set of technologies in 2 columns. I simplified a little bit the work. In the column left, you have a set of technologies in the category acting humanly or acting rationally, and some of them are available today, and some of them may become available in the next few years. Whereas in the right column, you have what, on the same categories, you have what could be stretch goals or really out of range. So just take one of them and think about it and prepare the answer. I'm going to ask you in a couple of minutes what you think. Who would like to start?
What is the question?
The question is, if you take one of these technologies which are here, which one is available today and which one could be available in the next few years, and if you take these ones, which one seems to you a stretch goal or which one seems to be completely out of range? Take one or two. Yes, go ahead.
Consciousness definitely has a range.
Okay. Yes?
Emotions too.
All right.
Natural language understanding is currently available now.
Okay.
Self-programming is also currently available.
All right.
Recommendation systems is available.
Yes, okay.
Teamwork is stretch code.
Teamwork, okay. Good, so let's see the answers. Do you agree? Issues? Yes.
With emotions, isn't it possible that they are ready for feeling or to answer like I'm sad and I mean I'm thinking about the movie Her
Yeah.
and I know it's out of print now, but I guess like it's happening in a way.
Yeah, it's a valid point. These are points of discussions. I put here the sort of conventional answers, but you can challenge this, of course, yes. Yes?
My point was too about the emotion, because I feel that it's something you can rationalize at some point, and you can teach someone to be happy, to be sad, with such criteria, the way he should react. And so
Yeah.
at some point, I guess you
But
can
would it mean that the system itself is sad or happy, or is it just answering a question?
If it's a robot, for instance, you can teach him to react as it were.
And understanding human emotions seems to be more possible.
Yes, you can actually detect emotions in text or in speech, or even in some images. You can detect if people express, if they're angry, if they're happy, or whatever. It doesn't always work, but at least it's
For
visible.
instance, in casinos, they are trying to develop these systems to organize if people are lying, their expression, the really traits of their faces.
Yeah, yeah. Okay. Yes?
Well, I think concerning the emotions, I think there's one point that is very important, which is hard for artificial intelligence to emit, is the physical level, because emotions, like most of the time, they are caused by some physical issues. So it's pretty much the facts that cannot be measured.
Yeah, that's right. That's right. There is the physical appearance of the machine itself may condition some.
Yeah, because there are some other reasons, for example, the environment and the atmosphere that sometimes cause you this or that emotions.
Right, right.
Yeah.
Yes.
But for all those 3 points that you mentioned that are out of range, doesn't it kind of depend on how you view our world? Because according to Elon Musk, he thinks that we are all this a simulation.
Yeah.
So if we can find the chemicals that kind of determines our consciousness, it's just like an algorithm.
These are, the reason I did put this is to trigger the discussion. I don't pretend having any of these answers. It's just because, in your day-to-day life, in your business life and so on, you're going to be actually dealing with this sometimes and say, okay, how elaborated is this particular system? Is this a system really displaying emotions, or maybe I'm fooled by something, but it's important to think about these things and when dealing with such systems. Yes?
Why do you think the natural language understanding will be a stretch code not in the next few years?
I'm coming to this. Open problems with AI. Do you know any system which is capable of answering this question? Is it going to be dark today when going back home? No. There is probably no system which can answer this question because you have no landmarks. However, the system, your phone has everything here to answer the question. Your phone knows where you are, who you are, maybe your agenda knows, since the phone knows the day and where you are when it's going to be dark, it's very easy, and knows where home is for you. So everything is there, but the semantic of this question doesn't show any landmarks that the system can really catch somewhere. So it's a very difficult question to answer. And most of the system cannot deal with such vague, in quotes, questions. The second thing, which is still an open problem, is situations when common sense is involved. We humans have a lot of common sense based on past experiences. We build a huge amount of context in our life, And for example, if you show me the video of this course and there is a giraffe sitting here, I know something is wrong, somebody did put the giraffe as a editing from an editing platform or whatever. The system would not probably have any problem with this. Or a car upside down on the road and so on. So there is a huge amount of things which are obvious for us that any 3-year-old would say, oh, that's not possible. But which for a system, for example, an object is falling. If I drop this object, it's going to fall down, not up, and so on and so forth. And we deal with this every day. But the systems today have to learn this somehow, but it's hard to teach such things. The other thing is that we learn, yes?
Like a falling object. Why can't a machine learn that every time an object is falling, it's going to the floor?
Yeah.
It can learn that?
It can learn. But how many rules do you have to learn like this?
What is physics, no?
You can, if you put 10,000 videos with a falling object, probably your system will learn this, and when it sees an object falling, it's going to be, oh yeah, something is falling. But then there is the issue of learning with very little training. So, for example, if you show to a young kid, a helicopter 3 or 4 times, the kid is going to recognize a helicopter. Whereas a machine learning system, you have to show 10,000 helicopters, and you're still not sure whether it's going to be fine. Because if I'm sitting beside the helicopter, maybe the whole thing was wrong. So little training is also an issue. Yes.
I would like to argue against this because
Yes.
there is reinforcement learning.
Yes.
So for a computer, it takes just as long to learn it 10,000 times as a kid 3 or 4 times.
Maybe.
So, like, if you're familiar with AlphaGo Zero,
Yeah.
it learned the game from scratch by
Right.
teaching it to itself, and it's
Yeah.
better than the AlphaGo, which beat world champions.
Yeah. Yeah, you're right. There are some avenues to solve these things, and some people are working on this.
So computers can learn faster than humans and in a shorter time span.
Yes, for some situations.
For some situations.
Which are games which have a closed environment in which the rules are very strict. You cannot actually drop one of the little pieces upside and get it on the other side of the board. Yeah. Yes?
Sorry, what is Alpha?
AlphaGo is a computer AI that plays the Chinese game of Go. I'm not sure if you're familiar with it. Yes.
Japanese.
And
East Asia.
Is it not Chinese?
It's East Asia. Korea.
Fine, it's Asian game. And it beat the world champions by basically learning from other players. And then you have AlphaGo Zero, who taught the game to itself by playing against itself thousands of times, and is currently the best AI.
Yeah, these are called reinforcement systems. These are systems where you don't learn you learn only at the end of the game, if you won or if you lost.
Yeah.
And so, which means that you play a long time, and it's only by playing millions of times that the system will learn actually, but each point of data is actually a whole play, whether the end result is yes or no.
It says Chinese, by the way.
Okay.
And Google developed.
Just before we go for the break, there is also an issue with robotics. For those of you who saw the film Ex Machina, you probably saw that the robot was actually very, very elaborated. But still, if you think about robotics today, are we able to build a bee or any insect and have the device behave with so little energy and so many times, 20,000 flaps per minute and so on with a piece of honey. So it's a challenge. It's a challenge. Today the robotic systems are still very big, consuming a lot of energy, cumbersome, and there are lots of things to deal with. And then last but not least, ethics and regulations. Today the regulations are just starting to happen. We are a little bit like at the beginning of the automobile, where there were no regulations, and according to the the number of automobiles introduced and the issues, the states came back with regulations and rules. But you know, in the early years of the last century, there were no rules on the road. No, you didn't have to drive on the right side. There were no traffic lights. Pedestrians were at risk, and so on and so forth. So it's here we are still in a situation where a regulation are being introduced, and we're at the beginning of this.
Sir?
Oh, yes.
So do you think the newly adopted GDPR will restrict the development of AI in the future?
Well, it's hard to tell. It's certainly going to give some rules to the people, which is good. It's better to have rules. So,
Can you repeat?
yes, the new
GDPR,
which are the, I don't remember this acronym, but it's a set of rules which are being adopted by EU, I guess.
the General Data Protection Regulation.
General Data Protection Regulation. Okay, thank you. So, well, regulation has to happen because then it would actually give guidance to some of the people. Now, whether the first regulation is a good one or it has to be adjusted across the years and so on, is an open question, of course. But, you know, if it's concerning more and more people, it has to be somehow regulated. Okay, good. If there are no other questions, we can go for the break. How long should be the break?
What do you guys think, 15 minutes?
Okay, very good. So see you in 10 minutes. Okay, good. All right, so in this second part, I'm going to run through a few slides explaining how the mechanics of machine learning works. It's a bit technical, so I don't expect that we will cover everything, but there is also material in these slides which is for you to look as homework. Especially there is a playground which is made by Google where you can actually simulate a machine learning system online. It's very easy to use. I'm going to show it to you. And I encourage you to, after this class, to use it and get more into this. And then we are going to have another business discussion on a few things, especially the way companies implement AI and what are the differentiation factors in the way people implement AI. Okay, let's start with some basics. There are a few terms that you should know in business which are important to remember. In machine learning, you have two tasks, regression or classification. Regression, you're trying to predict a value. For example, you have a stock value, you're trying to predict whether this value is, how much it's going to be in tomorrow or in next week. It's a value, it's a number. Then you have classification. Here you're trying to predict a category. We saw that we could, out of an email, predict whether it's spam or not spam. This is a category. You could actually do this by looking at some map and try to predict whether a place is a good place for agriculture or is a good place for residential and so on. These are categories. Okay, so these are the two tasks, regression, classification. And then you have three different machine learning methods. One is called supervised learning. This is what we have done with the UBS Mortgage Calculator. We have some training data, which is past decisions made by our colleagues or data where the decision is known and that we're using as training data. We teach the system using this data, and then the system is doing predictions or classification, and we test the system. So this is supervised learning with supervision using label data. And unsupervised learning, you have no training set. So for example, if you're doing, let us assume you're doing sentiment analysis in a system for for online maintenance. So one way, you have a product, you have launched a product, and then you are checking on Twitter what people are saying about the product. And you're trying to find if there are some patterns. You know, for example, this piece is broken, or I try to use this functionality, it doesn't work, and so on and so forth. Initially, you have no training data, but you're trying to build your knowledge across the time. So it's called unsupervised learning. And here you're doing clustering of your data, but in the beginning you don't know the clusters. And after some time you know that there is a cluster of people talking about this functionality or something which doesn't work, or something that they find with their distributor, or etc. So it's called unsupervised learning. It's harder, but you still have systems which work. And last but not least, you have what are called the reinforcement systems, what DeepMind does with the games. Here you have a system where you are teaching a computer to play a game, but the outcome of this game is known at the last second. For example, if the computer is playing chess or Atari, it's at the end of the game that the game was won or lost by the computer. So the computer is having a series of actions, and then at the end there is the verdict, there is the outcome, which is, you know, you won or you lost. So this is called a reinforcement learning. Okay. Now, to measure whether a machine learning system is doing a good job or not, you need to compute a loss. What is a loss function? The loss is the penalty for a prediction which is incorrect. So let us assume here on the left-hand side that you have X, a series of features, and using these features you're predicting the value of Y, which are the dots, you know, the little dots here, the beige dots. And the real value is, in fact, along the blue line. Let us assume that you're in this situation where you have the samples, which are here, but their real value is along the blue line. So the loss you're doing is actually the sum of the difference between the real value and the predicted value. These are the red arrows, you know, the length of the red arrows. These are the individual losses, and your loss function is just the sum of these individual losses. If you're doing this on another example, here you have the beige dots, which are your predicted values. Your real value are along the blue line, and you have this other loss function, and here the loss is lower because the sum of this length of the red arrows is actually smaller. So the loss function is something that your system is going to try to minimize. And to minimize the loss function, actually what is going to happen is that the system will actually proceed stepwise. The system will start, let us take this problem, the linear approximation that we had before. Let's take this, you know, this system. And we want to compute a loss. So we are going to have a first line here, which I did put in green, where we are going to have some loss. Okay? And we are going to see that this loss has a given value, but we want to optimize this. So we are going to change the parameter of this line and go to the line number 2, which is here. And with this line number 2, we are going to have a loss which will be a little bit lower. If it's not the case, then we'll take another line until the loss is lower. But you know, we are going to be here where according to the parameters of this straight line, we are going to have a lower loss. And then we'll continue this until we get almost until the loss would not evolve anymore. You know, that's reaches minimum value, which is this line number 3 here. And here will be at sort of minimum of the loss function according to the parameters, which are the slope and which are the 2 parameters of this straight line. Okay? So this is how the machine learning system proceeds. Stepwise, it's called the gradient descent. And each of these little steps that we did by changing the parameters is called a gradient step. And this is how they work. So you have the features, and you actually compute the parameter updates, and you do loops of this until the loss is the minimum. That's how it works. So it's really, so to give you another snapshot of the same, you have the loss function, which is here. Here you have the weight, if it's the slope of the straight line. And you start with the starting point here where you have a loss. And then you change a little bit the parameter of the straight line. You change it here a little bit, and you are going to have another loss, which is lower. Okay? Then you are going to continue until you reach the lowest possible loss, and which is going to be here. Okay? Now, you have two cases where things can go wrong. If on the left-hand side on the top here, you take two small steps, then it takes forever to converge. But if you take two large steps, then it would bounce across the line and you don't converge either, which means that the steps you are taking or the learning steps have to be moderate. And this is something experimental. There is no theory or math about this. You just have to experiment and see how your loss function would behave. Okay? So that's about how they work. The other thing is that here we have seen that we try to have the data according to a real value, which is a straight line. But we could be more sophisticated, because here you see that the loss function is going to be relatively high, because all these individual distances have some value, and the total is relatively high. We could have another function which is more adapting here, which would be a square, a polynomial function of second order, third order, and we would have this. This would be better for the loss. And we could be even, adapting to our training data and just going through each point with a very complicated function. But this doesn't work, because if you have some new data for the prediction, you will find that you have a huge loss, because this is not representing what's going on, really. So you better have something in between, which is neither underfitting or overfitting. And so the model complexity has to have some middle value between, having too much error because the model is too simple, or too much error because the model is too complicated. So this is how it works. This is really what people are implementing. Now I want to introduce you to a playground, which is called the TensorFlow playground.
Has anyone heard about TensorFlow? Programming AI program by Google. It's widely used in the industry now. I think the fake app you mentioned is based on TensorFlow. Yeah.
Okay. So,
and that's the playground part. It's a part that you can play with.
Okay, so in the interest of time and our session, I don't want to go too much in the details, but I want to show you a little bit how it works. Here we have a data set. It's online, so playground.tensorflow.org. You are here, and you can choose the data set. And here I've chosen this one, where obviously these two parts are separated by a straight line here. It's a very simple example, but it helps to actually understand and run the system. Here we're going to have one neuron, one unit, and the features are going to be, this one and this one. Just very simple data set. And if we look at activation, we put linear just to have something linear. And you see here, it does not do a good job, so let's run this. So it's going to do the gradient descent for each step. So one step is here. You see the separation is already not bad. You see the loss function, which is going down. Now a second step. Here, the loss function doesn't evolve anymore. The separation is a clean cut. The job is done. After 2 iterations, this was done. Now, if we add some noise to get the system a little bit more complicated, so here you see that we have a situation where things are not that clean, and there might be a separation here, but the data is not very good. So let's run this. So you see It's converging, and after 5, 6 iterations, it's coming to a loss which is stable, and you have a clean cut here. So these are simple examples. Let me show you another one, which is this one. Sorry. Okay, so here we have a situation where the data is actually spread across here. And if we are trying to do a linear separation, well, intuitively, it's not going to be great. So let's run this and see what happens. Well, you see that the system has a hard time to come to a decision. And if we run it faster and do lots of iteration, well, it doesn't converge, doesn't find a good curve. OK, so how can we...
Maybe just take the time to explain each metric that you're showing, the target loss,
okay.
the different features, and
yeah. Okay, so here we have a situation. Our data set is split into 2 categories, and we would like to find with one straight line, we would like to differentiate these 2 categories. Obviously, this will not be the case because there is no straight line differentiating these 2 categories. If I put it here, it's, you know, I can't really share the blue and the yellow dots. So nevertheless, I'm going to run this model. So you see here the loss is 0.5 in the beginning, and I use as features x1 and x2, which are the 2 coordinates here. So let me run this 1 iteration. You see that it's a bit better. My loss is going down, but I'm still at 0.949, which, and really there is no, you see that there is a straight line here, but it's not that obvious. I'm sorry, it shows on my computer, but not on the projector, but there is a sort of line here, but which is pretty blurred. And then I'm continuing, and you see that, you know, I'm keeping this high loss of 0.5, and really there is no, the line is not a real clear cut. So the system has a hard time to find, to converge. It's like, you know, it would bounce. Okay, now if we want to solve this problem, we need to introduce another features, because obviously with only the coordinates x1 and x2, it will not converge. So one way is to mix the features and say, okay, it looks a lot like if we multiply x1 by x2, the 2 coordinates, well, we might have quadrant where x1 times x2 is equal 1, and here equals -1. So if we do this and take x1 times x2, then we can start, and we see that the system is converging rapidly to differentiate the 2 things. But this is not linear anymore. You see? It's linear according to the product of the 2 features, and you have to do the segmentation. But it's not taking linearly these 2 things anymore. So this is how you can use the system, TensorFlow, and yeah, good. So we have done the linear classification. We have done this. Yeah. One thing, I'm going to step back a little bit and talk to you about some other data sets, because I've shown you some very simple data sets. But let me show you quickly what people have been using as data sets. First, before I'm talking about this, data sets are very important to prepare. And if you look at a typical machine learning task, the preparation of the data is 70% of the time. Cleaning the data, making sure that there is no mistake, there are not outliers, missing values, misspell, and so on, 70% of the time. 10% machine learning algorithm, running what I've just done, and 20% interpretation and visualization. So this is the usual split. And preparing the data is really key. Okay, let me show you some data sets that people have been using to tune machine learning system. This is one of the database to do handwritten digit recognition with 60,000 examples. This is a 0, this is a 2. This is another data set with about 500,000 instances. You see letters from A to J with lots of ways to actually print or display them. So these are a test set that people have been using. And usually the preparation of the data means putting the data in squares, values from minus 0.5 to plus 0.5, what we have seen before, having zero mean value. So these are some of the things people have to do.
And check the CAPTCHA technology that everybody's been using, sometimes not even without knowing what it was, it's based on this. Or it's actually helping this exist. The fact that people, the CAPTCHA.
Yeah, I know. Yeah.
You're trying to identify yourself letters. This is actually helping this machine learning system improve.
I don't know.
Is it plugged in together or?
No, I'm not sure.
Okay, it's just separate.
Yeah.
I know a lot of companies have been using it to.
Yeah.
Google's been using it to improve its.
Yeah, because if you look at these things, they're weird, but they're not as weird as the CAPTCHA. Because in the CAPTCHA, you interleave the characters. Let me explain. So, for example, instead of having in A and B, in CAPTCHA you would have an A like this and then a B like this. You see? And only a human would be able to say there is A and B because this system doesn't make it. It has to have the letters really separated. Otherwise, it's going to produce bad results. Okay, so I'm going to show you a couple of results obtained with some methods. Also point you to some ways of using the TensorFlow playground, and then we'll talk more about business. So hang on, still a few minutes on the tech side. Okay, KNN classifier, the one we used at the previous part on NIST. Well, I've run this with about 1,000 examples, accuracy 83% with k = 5. 83% is good and bad. It's okay, it works, but it means that 17% of the time it's wrong, which means that if you do character classification, if you do character recognition, it's 2 characters out of 10 which are wrong. It's a lot of mistake. Unacceptable for any business application. So on one hand it works, on the other hand, it cannot be solved. Good. Now, what people have been using is more sophisticated than KNN or the linear classification that we just saw. It's called logistic classifier. And this is, I'm not going to go into the math of this. I really recommend that you would actually look a little bit at this outside of this session. But this is what would compose a single neuron. And then, using the logistic classification, you can actually build neural networks. Think exactly as the linear classifier, perhaps a little bit more sophisticated, but you are going to stack this little classifier. Okay, so let me show you now neural networks. All right. This was the linear classifier where you would take the actual inputs, you would calculate the loss function and get the output and have this, 3 iterations. This is what we have done. Now we are going to replicate this in many places and do layers. So each of this one would be an actual neuron that we are going to stack in layers, and we are going to take many layers in order to solve a problem. So what does it do? If we look at computer vision, especially, for example, recognition of face recognition, a computer vision problem, then what you will find is that the first layer is going to find edges. So what you are going to get at the output of the first neuron are going to be edges. These edges are going to be fed in the second layers and then are going to be combined in pieces of the face. And then these pieces are going to be combined in the next layer into actually things which look more like a face, and at the end you will be able to make a decision whether this face is actually one of your employee or not, if this was the photograph scan at the entrance of your company building. So this is how this system works. You have layers, and each layer is capable of finding some patterns, and this pattern they get more and more sophisticated as we go deeper. That's why it's called deep neural network. All right, so I will show you just on the TensorFlow playground. I'm going just to show you how this networks can actually solve problems. So I'm going to put 2 layers, 4 and 2. So here we are going to okay. So we are going to try to differentiate between these two sets of data, the blue dots and then the pink dots. And you are going to see what each neuron is actually calculating here. So let me start the... You've seen? It would converge. We did 157 iterations of what I showed you, the gradient descent, on this Mac. This is not on the cloud. This is on the Mac. I'm going to redo it step by step. So you see in the beginning, the loss function is actually still at a pretty high level. But then you can see that each neuron here is starting to recognize some patterns which are not obvious in the beginning. But as you go, this is becoming more clear. Look at this. Here we are at a stage where you have one neuron detecting this, one neuron detecting that, one neuron detecting this piece, and here you start to have some little shape which are showing up. And if I run this up to the end, you see that each of these neurons is calculating a little edge. That's what I showed today at the first layer. But at the second layer, when you combine these edges together, you get this and you get that. And that's how you detect your two things, with 270 iterations of the gradient descent. So you see the power of this. Very powerful. And again, I recommend you start playing with this and try to really play with it. It's a nice sandbox. Okay. So one thing you need to keep in mind when dealing with neural network is that the way the parameters, the number of layers and how many neurons you have in each layer, you have a part of chemistry and a part of alchemy. Do you know the difference between alchemy and chemistry? All right. Alchemist. Medieval forerunner of chemistry based on the supposed transformation of matter. It was concerned particularly with attempts to convert base metals to gold and to find a universal auxiliary. A seemingly magically process of transformation, creation, or combination. And you see the guy who is trying to get his metal into gold in his middle-age playground. Okay, and here chemistry, branch of science, deals with the identification of substances of which matter is composed, investigation of their properties, the way in which they interact, combine, and change, and the use of these processes to form new substances. So much more scientific, much more structured, much more, etc. So today, neural networks are a bit of both, which means that you remember the Normalization, this character recognition. If you run a neural network with one layer of 512, you have 4,000 nodes over there, and you run this, and you get to 94% of accuracy. If you run with 2 layers, the best result you can get here with 512 nodes on the first layer and 250 nodes on the second layer is 95.6 accuracy, percent accuracy. But on the Mac, this is about 2,000 seconds, which is almost a good half hour. So this is what you can do on the Mac, more or less, but there are already many parameters. But if you look in the literature, you will find that some people did much better. And this time with this example, you have this guy who did a 6-layer neural network, and here are the number of nodes: 784, 2500, 2000, 1500, 1000, 510, and 0.35% error rate. How did this guy get this? Test and trial, feeding the computer nights long with lots, I mean, not his computer, but a cloud, a data center with lots of test cases, trying to understand why he would get 0.5% and so on and so forth. Some chemistry, because obviously understanding how this works, but some alchemy as well, putting the things together until, something meaningful would come. And that's called, and that's a little bit how neural networks are tuned these days in the industry. People spend weeks, teams of engineers, they spend weeks, tweaking the parameters, running this, changing the number of layers, changing the number of nodes in a layer, running it again and again and again. And after 3 months, they go to their director and say, now it works. And then the question is, why? Well, we tuned the parameters. There was a little bit of course, of engineering and scientific background, but we did a lot of experimental work. And that's what's happening today. Okay? So deep learning, as I mentioned before, is used for face recognition, more fun. It's used to do artwork. Here you have a picture. Here you have a painting from Van Gogh. And if you use neural network to predict what would be this picture by Van Gogh, is what you get. Here's a picture. Here's another more recent painting. And here is what you would get.
This is what Prisma used to do.
Sorry?
The application Prisma.
Yeah. It's exactly this. Okay? So now let me switch to AI development in the industry.
And Michel, just to interrupt, last summer Google Arts and Culture, which is a department within Google, used this technology. Actually, it was 2 or 3 months ago, and they launched a US campaign whereby you'd send your picture, and they would find in all of the art collection that Google has been scanning, they would find the one portrait in art history that actually looks closest to you. And obviously it went viral, and it's a great way to popularize arts and culture, obviously. So AI also has this power. The legal reasons, they only launched it in the US for now.
All right, so now we are going to talk a little bit about the AI development in industry, and there are 3 important business factors I would like to mention, and then we'll go through some companies which I have intentionally clustered using some, not neural network, but using some common ground for them. Okay, so 3 factors. Scaling. The size of the data sets would tell you how far a company is going into using AI and machine learning. If people, for example, for recommendation systems, if you look at the retailer would have tens of thousands of products, millions of customers, and then this is this huge matrix which is almost empty because not every customer would buy every product, but each customer would buy a few products only. So if you do this table where you have the products and the customers, it's almost empty, but you have some spots here and there. And out of that, you're trying to find some patterns, some preferences, etc., for recommendation. So scaling is very important. You can have an algorithm which works well on hundreds or thousands of examples. It doesn't mean that it would work well on millions of billions of examples. And that's a key differentiator factor in the business. Is the company able to scale in terms of the analysis? So that's very important. Then you have another thing, which is the following. Most companies in the internet space, Google, Amazon, Facebook, are actually doing products for the consumer. And these products are actually tuned and developed with the mission of being good enough. Let me explain. If you are looking for a pizzeria nearby, you are going to get some results based on your preferences or recommendation system. If you don't like this choice, or you find it a little bit not really matching your taste or whatever, or your preferences, you're going to be slightly irritated, maybe somehow irritated. But for the designer of the system, if the number of people irritated by this choice is lower than 2% or 5%, it's okay. It's okay, they won't go, but the other would go, or the ad would be actually well targeted for the other. So it's called good enough. And most of the applications that you have today for consumers are good enough. Whereas if you look at other applications, such as the detection of a disease or the security system of a large manufacturing plant, then you cannot have good enough. If a doctor is showing you a picture and some measurement and say, yeah, you may have this disease, 90% of chances or 95, it's good enough, and cannot explain how the result came, and second, how the 5 or 10% error rate, then, for something which is mission critical, the system is not good. So some companies have more a mission critical approach, and these are more traditional companies like IBM, perhaps Oracle, HP, which are coming from the enterprise, which are not selling product to consumers, but to the enterprise, and are seasoned with mission critical. For example, the data centers that IBM or HP or Oracle would sell you, they have mean time between failure of 5 nines. The disks are up and running 99.59% of the time, which means that in the data center where you have 10,000 disks, only one disk would fail in so many days, and so on. So these are the mission critical measurement that industry wants. So which means that in the deployment of AI, you should consider what is good enough, but still very interesting for some businesses, and what is mission critical and which has to adapt to other businesses. So that's the second factor. The third factor is the do-it-yourself versus use machine learning or AI as a service. Is data a strategic asset for your company? Can data be transferred to any cloud service outside of your company? Are you allowed to do this? Can you do it? Do you want to do it? Is it better to use a model created by a service company or programming internally? Make versus buy. So these are very important decisions. And this is another business factor to keep in mind when looking at the business of AI. So if you look at the internet companies, they're very active in recommendations, in being able to address billions of users with virtual assistants, with customer preferences, forecasts, intelligence on the keyboard, speech recognition, image recognition. In China, you have the equivalent of the US companies with Baidu, Alibaba, Tencent, etc. But all these companies are consumer-oriented with good enough solutions. Some of these companies are doing some effort and are trying to move into the mission critical, but they have not started from there, and the jury could be still out to check whether they are going to be successful or not with, mission critical application in industry, in medical health applications, in insurance applications, and so on. So this is the one category. Then on the other hand, you have companies like IBM, HP, Oracle, Intel, Cisco, which are coming from the enterprise. They are not selling products to consumers, except HP, which has been selling PCs and printers to consumers, but also to enterprises. And Watson, for example, is enterprise focused, is addressing mission critical things. And IBM is really working very hard to make this mission critical task successful. So it's a different business, a different market. And also one can say that these companies are not today and are not likely in the short run to have good enough solutions for consumers. So you have really a sort of separation of the business into two categories. So for example, you have Intel, which has a neural network processor with self-learning chips, etc. Cisco first predictive services powered by AI for its networking gears. So this is an enterprise application as well to do predictive maintenance. These are important mission critical applications. All right. Now, another category is companies which are coming from another which have another business which has nothing to do with IT, with AI, but which are more and more using AI. The move towards cars which are becoming more and more autonomous is actually triggering many companies like BMW, Toyota, not even talking about Tesla, to actually hire engineers and scientists to do AI in order to, for example, BMW is hiring half of its engineers as software engineers, which is unusual for a car company. So you have huge efforts which are made with GM data centers, chips for self-driving cars, and as I mentioned, increase in hiring of software engineers. Cars are more and more seen as vehicles to acquire data acquisition engines. And these companies are currently thinking about business models based on the data that cars are going to collect and check what can be done about this. The car is more and more a commodity which has to actually acquire a lot of data. Last but not least, there are even more ambitious projects like the pilotless planes of Airbus. In the hospitality business, it's actually an industry which got very disrupted by AI recommendation system. Booking.com, its competitive advantage is a marvelous recommendation system, which is beating most of its competitors because they could tweak the algorithms, they have the right data, and they can use this to be really on the edge. The other ones.
Hospitality transfers. 10, 5 now.
So I think it's important in this business to really understand the business model of companies like Booking, eBookers, hotels, TripAdvisor, etc., because they're not going to buy all the hotels of the world, of course, but on the other hand, they act as disintermediation agents to actually get the data about the customer, get the data about the hotels and the resorts and facilities, and reconcile this in order to optimize the business. Whereas if you are sitting on this end of the chain or the other, it's much harder to get the whole value chain. And the Uber model is very interesting in this sense because you have a double recommendation system, and that's what makes the model very powerful, is that on one hand, the customer would judge whether the Uber driver was good or not, but the Uber driver also judged whether the customer was decent or was problematic or whatever. So recommendation systems are really disrupting a lot this many hospitality-related business. The trend is to have more AI, chatbots, customer data processing, and one of the trends which is very important as well is on-the-fly customer preferences, which means being able to make decisions very fast and not wait until you have 3 months of database and data collection about customers to actually change the offer. This, for example, the EasyJet model, business model, where they make decision on the fly for prices, which many other companies are trying now to replicate or to implement. So these are some of the advantages of AI. Under the hood, what you have a neural network, and then you have very large vectors for customers, and you feed the neural network, which is actually all the time giving some insights or recommendations, etc. Which can be price, which can be special offers, which can be target customers, which can be recommendations for particular products, and so on. So this really disrupts the whole business. Any question on this? No? Clear? Okay, good. You have also many other companies which would be unusual there. Shell, for example, has been using its own virtual assistant to handle about lots of products and offers to distributors. And that's, you see the numbers here, they're really important, and they allow really Shell to have a better positioning in its business. MedTech, we talked about some of the challenges. Here you're dealing with really mission critical things, whereas in the hospitality business you were more on the consumer side. Here you're really, and FinTech is probably more on the mission critical thing side as well, where the impact of bad decisions is probably less than in the MedTech, but still cannot be accepted as good enough. All right, I will finish by 5 predictions made by Forbes for artificial intelligence. Data-driven machines, more human-like help, Siri and other tech will hear you better, smart automation, and AI adoption. So these are some of the trends.